Hi everyone, thank you for attending to this webinar. My name is Yusuf Alawi and I will run this presentation on footfall analysis. In this webinar, we're going to talk about the theoretical background, basics of the dynamic analysis, modal analysis, and then we will go through footfall analysis. And in the end of this session, I will run some examples in FEM-Design. So let's start. In this slide, you can see the basic equation of motion. It is in its general form for force vibration. It contains mass matrix, stiffness matrix, and damping matrix, as you can see in this slide. During the analysis, the mass matrix is always constant. The stiffness matrix, on the other hand, is only constant for linear calculation and not for non-linear calculations. In the dynamic modal analysis, we simplify the previous basic equation of motion by setting both damping matrix and load vector to 0, as shown in this slide. Then the previous equation of motion will be reduced to equation number 2, and this equation is called undamped free vibration. After further more simplifications, we will get equation number 3, as you can see in the middle of the slide. This equation is called Eigen Equation. By solving this as an eigenvalue problem, we get two types of results. Eigenvalues, which is the frequency of the structure, and the other one is eigenvector, mode shape, which is called also mode shape. Eigenanalysis is used to determine the basic dynamic characteristic of a structure. The result of an eigenvalue analysis indicate the frequencies and the shapes at which a structure naturally tends to vibrate. Although the result of an eigenvalue analysis are not based on a specific loading, they can be used to predict the effect of applying various dynamic loads. Now let's jump to footfall analysis. The aim of this type of analysis is to evaluate vertical response in structure nodes that is induced by harmonic force. This type of analysis is code-based, and for that reason I want to show you the implemented references in FEM-Design. As shown in this slide, the implementation of footfall analysis is based on the points presented below. And we have also used additional data from Concrete Center. Footfall analysis is based on harmonic sinusoidal force input. However, instead of using a single sinusoidal forcing, which unlikely occurs in practice, a more complicated continuous forcing function is used to establish overall response. This function can be broken into a series of sine waves, each of which has a frequency at integer multiple or harmonic of the forcing frequency. Each harmonic will have an associated amplitude and phase shift, and the set of harmonics are known as Fourier series. In FEM-Design, there are different options to set the required Fourier coefficients. There are different number of harmonics for different options. For example, according to the Concrete Center table, we have total 4 harmonics. The user can also manually apply up to 6 arbitrary Fourier coefficients. As you see, for each harmonic, you will have each harmonic has own design value of coefficient, if you see the column to the right. In top of this slide, we can see a diagram showing harmonics of Fourier series for low impact aerobics with 4 harmonics, plus a statical force corresponding to the weight of a person and the total force value. Notice that the amplitude of each subsequent harmonic is lower. This shows that the most energy goes to the first few harmonics. If we focus on the thick black line named total force, we can see that the force does not follow the half sine wave shape. This is a very good illustration on how we went from a complex force function to a series of sine waves. To the right, we can see the amplitude of the harmonic force, denoted as Fh, equal to alpha h into q. Alpha h is the Fourier coefficient of the h harmonic, also known as dynamic load factor. And q is the static force exerted by an average person. For each harmonic, the amplitude of dynamic force is expressed as a fraction of a person's static weight. The dynamic response of footfall-induced vibration can be split in two parts, called transient and steady-state vibration. The transient vibration can be described as a series of damped free vibrational response of the system, as you can see in the graph to the left. In the graph to the right, you can see the steady-state vibration when the response of waveforms have settled down. The response factor for footfall analysis is calculated using two different types of analysis: resonance response and transient response. Resonant response occurs for low frequency structures. So in this case, if a structure have a relative low stiffness, then the steady state is more significant, and the transient is negligible. Transient response occurs generally for high frequency structures. So in the case if the structure is relatively stiff, then the transient response will be more significant than the steady state. It is also assumed that the resonant response can be induced up to fourth multiplication of the walking frequency. So for example, when the maximum walking frequency is about 2.5 Hz, the limit for resonance possibility is about 10 Hz of the basic natural frequency. Here we can see the acceleration results yielded from an example, visualized in the graph to the left. We can see two distinct lines. The red line represents the steady state response, and the green line represents the transient response. If we look closer at the graph, we can see that this function has formed a series of peaks, with each peak corresponding to the natural frequency of the structure. The peak values appears when the eigenfrequency of the structure is equal to excitation frequency or its harmonic. This is a very important, I'm going to say it again, the peak values appears when the eigenfrequency of the structure is equal to excitation frequency or its harmonic. This form is called resonance. I will show you in when we run some examples in FEM-Design what I mean by that. In FEM-Design, there are many ways to describe calculated vibration behavior of the structure. One is the acceleration, as I mentioned before, but we can also see the result as dynamic amplification or response factor. Before we go into more details about the types of results, I would like to explain the three types of excitation modes. The first mode is called self-excitation, which analyzes the response in the same node to which the force is applied. So, this means that the concentrated excitation force is applied if it is applied in node number 1, as shown in the top picture, then the response will be calculated in node number 1. The second method is called full excitation, which analyzes the response in any node to the effect of the force applied to another node. So, For example, if the excitation force is applied at node number 2, then the response will be calculated in all nodes based on the excitation force at node number 2. The third method is called rhythmic crowd load, which means that the excitation force can be distributed as a surface vertical force, also as a concentrated force or line distributed force. This type of excitation force is usually appropriate for induced vibration by small groups, like for example in event, dance event or aerobic event. In this excitation method, the calculation will not only be performed for the steady state, which usually have the most significant impact on the structure with regarding to this kind of events. As you know, the human response to vibration is usually measured in terms of acceleration, while the acceptance values are expressed in terms of response factor, which we will present in a moment. There are many ways that can be used to present the acceleration of system. However, the most obvious one is the largest acceleration, also known as the peak value. But the largest acceleration does not give any indication about the amount of time the system is subjected to this level of acceleration. So, instead of using the largest acceleration, in FEM-Design we use the root mean square acceleration, which is called RMS acceleration, as shown in the formula in the middle. In case of the sinusoidal signal, the RMS acceleration value is equal to the peak value divided by square root mean of 2, as seen in the top right corner. The RMS acceleration that will be used for yielding the response factor will be based on the max acceleration from either the transient or steady state. But as I mentioned before, for excitation mode called rhythmic crowd load, the calculation will only be performed for steady state. Other useful result is the dynamic magnification factor for displacement. The static deflection under this equivalent static load will be equal to the maximum displacement of the dynamic behavior of the structure under the rhythmic crowd load. This result is only provided for the excitation method known as rhythmic crowd load. These base curves represent the magnitude of building vibration in z-axis for approximately equal human response with respect to human annoyance and or complaints about interference with activities. Satisfactory vibration magnitudes in buildings should be specified in multiples of the base curve magnitudes. The area below the red line vibration, which are the area below the red line represent vibration which are imperceptible for the most people. The perception of vibration also depends on the frequency. As you can see, the humans have been found to be most sensitive to vibration of frequency between 4 to 8 Hz, as shown in the graph to the right. Human response to vibration is usually measured in terms of acceleration, and the acceptance values are expressed in terms of response factor R. In FEM-Design, the response factor is defined as the calculated RMS acceleration divided by 0.05, as you can see in this slide. So, for example, response factor of 1 corresponded to the magnitude of vibration just perceptible by typical human, while r equal to 2 correspond to vibration 2 times stronger than what perceptible. The limit values on the vibration response factor in different reference can be found in the tables below. Design values for response factors are given in British Standards 6472, but for certain circumstances, different values have been recommended by SCI. Values of hospital are defined in HTM 0801. There might be other circumstances where the client of the buildings specify lower limits on vibration response. For example, because of some particular items of equipment require it. In this slide, we have a recommendation for damping according to SCI P345 and the Danish Annex. Good to know, in FEM-Design, the input parameter for damping is the damping ratio. But in Danish Annex, the damping parameters is given as a logarithmic decrement. So in the equation in the bottom right, you have the illustration on how to go from logarithmic decrement to damping ratio. Now let's run some examples in FEM-Design. So before we do any footfall analysis, we go to the load tab and go to mass conversion. Here we have two different load cases, and I want to specify which load case I want to include in the eigenfrequency calculation. So in our case, I choose dead load, of course, by setting factor equal to 1 and click OK. The next step is to go to footfall analysis data, and here you have two different options. You can choose between self-excitation and full excitation. So in case we want to perform footfall analysis according to excitation method self-excitation, then we choose this one, click here, define, and we select the region we want to perform analysis on. So in our case, I'm going to select the whole structure. And in case you want to use excitation method called full excitation, you go and specify where you want to have your excitation force applied on the structure. So in our case, I'm gonna choose this point in the middle, and as you can see, you get a mark, green mark, as a symbol. The next steps is to go and check that you have sufficient number of your elements. In our case, we have 4. So to increase your quality of results on your results, you should increase the number of elements. So in our case, I'm gonna choose 8. And by increasing your number of elements, you will not, in this case, for this structure, you will not have a big impact on your calculation time. So the next step is to go to the analysis, and here we can see we have the eigenfrequency calculation and footfall analysis. Usually when we want to perform eigenfrequency calculations, we go always to here and check this box. But in our case, when we want to do footfall analysis, we go directly to this here, and we check this box. The eigenfrequency calculation will be performed, and they will only include mass in z direction. But before we do any analysis, we go to setup. Here, as we talked about before, we have different excitation method we can choose between. Here you have the number of footsteps. This parameter is only important for resonance response analysis. A lower number of footsteps reduce the possibility of resonance. More about how to choose the number of footsteps can be found in the reference SCI. And here you can define Walker's weight. Here you can choose between two different frequency weight factor. More information is provided in reference SCI. Here under the frequency data, we can define the frequency range by choosing the minimum and the maximum frequency. Here we have the frequency steps. This is important that we have a sufficient number of steps because it's here where we define the amount of frequencies that will be included in the calculations. So, for example, if you choose a frequency step equal to 2, then the response will only be calculated for frequency equal to 1 Hz, 1.9, and 2.8 Hz. So, of course, I will not have 2. I will increase it. Once again, for this structure, by increasing the frequency step, we will not have a big impact in the calculation time. And here we can put the damping factor. Here we have different reference that can be used for calculation of Fourier coefficients. So now we can start the footfall analysis and check the results. Here we can see, as expected, we can see the maximum acceleration in the middle point. We can go to footfall analysis and start by, I'm going to start by showing the vibration shapes. Here we can see that we have included 3 mode shapes in the calculations. And we can also visualize the mode shape. And here we can see the 2 results provided for this method, full excitation. So the acceleration in the middle point and the response factor. So if we choose display, then we will see the maximum acceleration is maximum in the point where we have applied the excitation force. So for more details, we can just click here and we will see the acceleration for both steady state and transient. Here I want to show you an interesting thing. If we see the peak values, like I told you before, the peak values appears when the eigenfrequency of the structure is equal to the excitation frequency or its harmonic. So if we go and see the first eigenmode, the first frequency is equal to 4.2. If we go back to the table, then we can ask ourselves, how can we get the peak value for frequency equal to 1 when our first frequency, natural frequency, is equal to 4.2. So as I mentioned before, if we go to the previous table here, we said the resonance will appear if the eigenfrequency of the structure is equal to the excitation frequency, which we can see for this example. The first harmonics, we have excitation frequency of 1, but the fourth harmonic, the frequency for the fourth harmonic will be 4. So in this case, here, the fourth harmonic will have the biggest impact on the structure. And for that reason, we have peaks. And the same phenomenon is explained for other peaks too. So now let us run the analysis for self-excitation and just click OK. And as I mentioned before, for this type of excitation method, we have two results, acceleration and response factor. In this case, the response factor is equal to 8.86. And the response factor is calculated with by dividing the RMS acceleration by 0.05. So now let us check the last example. Same thing here. You go and choose your load case you want to that's going to be used in eigenfrequency calculation. We have a crowd load as a surface load here. We go to the analysis, footfall, setup, and here we select the load case that's going to be used for excitation force. So here we have a crowd load. We select it by clicking here and just click on OK and perform. So now let us check the results. For this kind of excitation method, we have three different results instead. We have acceleration, we have response factor, and here in this column you can see the dynamic magnification factor, which is calculated for each eigenmode. So in this case, we have four different results, but I recommend you to choose the maximum value, which is for, in this case, for eigenmode 1. I hope you found this webinar interesting, and thank you for attention. And please feel free to send your questions to support.femdesign@